because we've got a lot of code to write. So, hi, my name is Jesse.
Hi, Jesse.
Awesome. I'm A.JesseJiryuDavis. I'm a staff engineer at MongoDB. I work in Python and in C. And this talk is going to be about how Python asynchronous coroutines work. And obligatory plug, I work for MongoDB. Everything I know I've learned there in the last 3 years. I wouldn't be speaking at conferences, contributing to open source if I weren't there. And I'm not the last person they'll hire, so you might be among the next. Go to bit.ly/mongo-jobs. It's been a really fulfilling place for me, and it might be for you as well. Additionally, I've got a landing page for you here with links out to a number of additional resources for the stuff that we're going to cover at breakneck pace today. So if you want to consume this information at leisure and go deeper, go to bit.ly/coroutines. So for this talk, I've created a dumbass web server. Start off with that. And all it does is it prints out a few hundred bytes of output. And besides being dumb, it's also slow. It takes about a second just to do this really dumb thing. So what we're going to do is we're going to optimize our client for downloading slow URLs, which after all is a very common problem in the world. Whenever you're talking over the internet, there's a high probability that the process at the other end is going to be pretty slow. So we're going to see why async optimizes for this problem. So let's get started. So let's say that we wanted to fetch this URL. So if we did that in Python, we would say, like, let's get a path. And first we would need to make a socket. And we would connect it to localhost on port 5000. And our request would be like, get the path HTTP1, and HTTP requests end in weird double carriage return and new line. And we'll stick the path in there. And then we just, send the request. We need to encode it. This is all going to be in Python 3. And then once we've sent the request, we'll just let's make a list of chunks, and then we'll receive chunks of up to 1,000 bytes at a time. And as long as there's a chunk, then we'll just add it to the list. And if there's no chunk, that means that the server has completed its response. And so that means that we can say, like, we'll join up all of those chunks using the empty byte as our quote delimiter, which is sort of like a delimiter at all. Decode that to UTF-8, or from UTF-8 to native strings, and then we'll just print that. So let's get that path and see how that goes. Great. So it prints out a bunch of junk. Oh, why? Oh, you probably see my problem here, which is that. Oh, don't crash on me. All right, hold on. Woo. This is going to be a good ad for PyCharm, but then it wasn't quite so much. I really need to file that, actually, because I keep hitting that. All right, great. The problem, obviously, is that I'm in an infinite loop. Great. And this font is really excessively large. Okay. So that works, right? And let's see out of curiosity how long that took. So let's auto import time, and that takes about a second, right? And by the way, I'm not like a godly programmer. I don't always type huge amounts of nearly flawless code. I've practiced this dozens of times, right? So just to be clear that this is not show off, this is magic trick, right? Magic tricks are rehearsed. So the problem with this code is that it takes, oh, and let's sort of like de-obscurify this a little bit by just printing out the first line, right? So I don't need the whole body. I can just say 2 headers, okay. And here's the problem is that it takes 2 seconds to download 2 URLs, and it's going to take 12 seconds to download 12 URLs. So this is the problem that we want to solve. And ordinarily, the way we would try to solve this problem is by launching a thread. And that would actually work great. Like, despite the global interpreter lock, the socket module drops the GIL whenever it's waiting for I/O. And so threads in Python are a perfectly reasonable way to get I/O concurrency, to do multiple I/O operations simultaneously. And that's what most web frameworks do, actually, is that they launch threads to do I/O. But this is an async talk. So let's see how async works. Async is built on non-blocking sockets. It's built on callbacks, and it has an event loop. So generally speaking, when we talk about async frameworks in Python, we're talking about this set of things that construct the framework together. So what do I mean by non-blocking socket? Well, it's a socket that you've set blocking false. Now, if I run this, this is not going to work. And the specific way that it's not going to work is that it will throw a blocking I/O error from connect. So I don't know. My sort of default way of dealing with problems is to ignore them. See what happens now. That default method usually doesn't work, but I always try it. So in a way, I made some progress. I got past the connect because I caught the blocking error. But the problem is that it said you're not allowed to send because the socket's not yet connected. So what we need is some way, and the reason, by the way, that this blocking I/O error is raised here is a non-blocking socket doesn't block. Every operation either succeeds immediately or raises an exception because it's not allowed to wait for some future moment when it can succeed. So that's why it raises an exception if you try to do something for which it's not yet ready. In this case, I'm trying to send on a socket, but it's not connected, so I can't send anything. So we need some way to wait for it to be connected before we attempt to send our GET request. Now, operating systems have ways to do this on non-blocking sockets. The oldest such function that I know of is called select, but there's also poll, epoll. On BSD, there's KQ. On Windows, there's I/O completion ports. There are various scalable ways of doing this. In Python 3.4, the nice thing is that we've got this selectors new package, new module, which just gives us whatever is best. So let's make one of those. And in order to wait for the socket to be connected, we'll say, I am interested in this socket, and I'll pass in the file number, which is just an integer. It's the file descriptor. It's probably like 4 in this case, because it's the first thing after standard error that I've opened. And the thing that I'm interested in is I'm interested in when the socket becomes writable, because that means that I can call send on it. So I'll say I'm interested in that, and now I'll wait for that to happen, and then once that happens, I'll unregister the socket, and now I can call send. So let's see what happens when I do this. Well, some progress. I've now gotten past connect, and I've gotten past send. But now I throw an exception in receive, another blocking I/O error. So I guess we could just do sort of the same little dance here. We can say I've sent a request to the server, and now I'm waiting for the server to respond to me, which means I'm waiting for the socket to become readable. I'm waiting for something to be available to read. So each time I want to receive on the socket, I'll say, tell me when the socket is readable, and then I'm going to wait for that, and then I'm going to unregister the socket again, and that means that I can receive something, or that there's nothing to receive, which means that the socket is closed. So we can run this, and it works again, but I haven't actually made any progress towards my goal, right? It still takes 2 seconds to download 2 URLs. All I've done is made my code a little hairier and more complex without actually winning anything in exchange. So great talk, Jesse. The next step is callbacks. We need some way to say, I want to do this next, but meanwhile, you can start on other work. And we express that continuation, the thing that I want to do next, by saying execute this callback when the thing I'm waiting for is ready. So let's see what I mean by that. What do we want to do when the socket is writable? We want to do this stuff, right? So let's put that stuff in its own function. And I'm going to call the function connected. This is what we're going to do when the socket is connected. And PyCharm kind of starts to lose its mind a little bit because path and s are no longer defined in this new function. So we're going to pass those in as arguments. And then up here, we want to define a callback. And what we're going to do is we're going to capture those data that we want to pass into the callback using a lambda as a closure. And that is a fancy way of just saying we're going to do this. Not that special. So we're going to then wait for the thing that we're waiting for, and when that's done, we're going to execute the callback. So far I've just made an even bigger mess, but at least it still works. But I still haven't made progress, right? The next thing I need to do, well, let's sort of continue this exercise, however pointless. And then we'll eventually see why this is going to pay off. So we've got the same problem here, right? We're registering, we're waiting for something to happen. So let's say once again that everything down here is what I want to do after the socket becomes readable. So we'll name this readable. And once again, we need to pass in the socket. And then the other thing that PyCharm is going to complain about is chunks. Chunks isn't defined down here. But we don't need the request anymore, right? We don't need the path. So let's pass in the chunks. Parens, thank you. OK, so this is what we're going to do once the socket becomes readable. And up here, we're going to define that callback sort of in the same way. It's going to be a lambda, and when we execute it, it's going to pass in the socket, and it's going to pass in the chunks. So this no longer should be a while loop, because we don't want to call the callback repeatedly. We just want to call it once when the socket becomes readable. So we'll do that here. And then we have one more time to do this laborious work, which is here. If we have a chunk, then we need to wait for the socket to become readable again, because that means that the server has sent us another chunk of data. So we'll do that here, right? So if we get it, so we unregister the socket, we get a chunk. If there is a chunk, we add it to our buffer. Then we redefine the callback, we re-register the socket, we wait again for the socket to become readable, and then we execute the callback that was waiting for that event to occur. So once again, not really making progress, but at least it still works. How do we actually make progress from here? How do we do these two fetches concurrently with each other in a single thread? Right? Once we do that, that will be async. We'll have achieved I/O concurrency. So I said that an async framework, it uses non-blocking sockets and callbacks. So the final piece of the puzzle here is the event loop that schedules callbacks to run interleaved as what they're waiting for completes. So we'll see that here. This is the event loop. And it just says forever. Tell me if anything happened. And did anything happen is returned as a thing called events. So I'm not sure what that is yet. So I'm just going to set a breakpoint there to figure out what that is. But meanwhile, we need some way for the event loop to know what to do next. We need some way to associate events with callbacks. So the selector module provides us a way to do that. And it's this secret argument that only hipsters know about. It's the hidden track. It's called data. And since this is Python, you can pass anything in here. So I'm going to pass in the callback. That's going to be the data that I associate with this socket and event. So when this event happens on this socket, this is the data that I want to be associated with that event sometime in the future. And then I'm not in charge anymore of calling select. That's now up to the event loop. And I'm also not in charge of executing the callback. That's up to the event loop as well. And we have two more places to do that, right? We need to do that when the socket becomes readable. And we need to do that when the socket becomes readable again. All right. So let's run this to the debugger. And let's just see. So we called get twice. It created two sockets, started those connecting. And then they left without finishing their work. And then we popped down here and we started executing this loop. I was hoping that I could go toward more like 440. I talked to James, I was asked to do that. Thank you. So we've got this events structure here. Let's see what's in there. So I'm going to inspect that. And we see that it's a list of length 2. Let's see what's in there. The first element of the list here, it's a tuple, it's a pair. Now, the second part of this pair, of this event object, it's just a mask, and it's just the number 2. It's just saying the thing you were waiting for, which is for the socket to become writable, that happened. That's just the value of event write is 2. So that's kind of boring, because that is exactly what I expect. It's not informative. But what is interesting is this selector key thingy, this named tuple. And what it's got is a data field, and check out what that data field has as its value. It's that lambda. It's my callback. So this is where it ended up. I registered it as the data, and it came back to me as the event data in this select loop, this event loop that I've got down here. So let's use that, right? So for the events was a list of key mask pairs. I don't care about the mask, but I'm very interested in key data because that's my callback. So that means that whatever the callback is waiting for is ready, so we'll run it. All right, so let's run that. And pretty good so far. We've succeeded, but we're still running because I've got another infinite loop. So let's say that we just want to loop while there's work to do. How are we going to do that? Let's say at first that there's no work to do. And then as soon as you tell me to get a path, that means that there's one more work to do. And if I'm down here and I received an empty chunk, that means there's no more work to do. So this return statement is no longer necessary. But what we do need to do down here is decrement tasks. So that'll go to 0 once the second callback chain runs to completion. Check it out. So that's pretty cool. And how about if we do it like a bunch of times? That's pretty cool, right? So why is that possible? How come I can scale out to dozens of concurrent requests without losing any time? It's because none of these requests requires significant computation. Overwhelmingly, this process is just waiting for my slow, dumb server to send it more chunks. So as soon as one of those events occurs, it can pretty much handle it before the next event. And that means that it's got a huge amount of wiggle room to do concurrent I/O processing, even though it's single-threaded, even though it's only using one CPU and it has no parallelism. So this is what async is great for. It can scale out to a very large number of things that it's waiting for, but not actually doing anything with. At some point, if you allocated a thread for each of these things you were waiting for, the threads themselves would start to take significant overhead. The memory, the operating system scheduler, the startup and shutdown costs of each of these threads would eventually start to cost you something. Async can scale out to a much larger number of concurrent I/O events that it's waiting for before the cost of these callbacks, right? That's all it's allocating, a callback and a socket. It can scale that set of data structures out much, much larger than it can scale out threads before the overhead of them starts to slow you down in any measurable way. So that's the kind of thing that async is good for. But unfortunately, it's also like an ungodly mess, right? It's hideous. We've taken what had been a very nice like 10-line example and we've exploded it out into this giant fussy piece of crud. So I have a promise for you, which is that we can recombine these three callbacks into a single generator. That'll be a coroutine. It'll be a single function. It will have all of the efficiency that we have right now with a lot of the simplicity of threaded programming. So that'll be coroutines. And coroutines are based on three things as well. Everything comes in threes. There's a future class. There are Python generators. and there's a class called task. Now, there are lots of things that are called coroutines. This is the kind of Python 3 async IO idea of what a coroutine is. So we'll start off with the future. We'll begin with the future. You'll just have to keep trusting me that this is leads towards an improvement, because at the moment it's just going to look like it makes things even worse. So it represents some future thing that we're waiting for. And when that future is resolved, when it happens, we run everybody who is waiting for it. And so instead of having explicit callbacks here, we'll wrap the callbacks in futures. So we create a future, we add this callback to the list of things waiting for the future, and then the future, rather than the callback directly, is what we pass in as the data here. And we have to make that transformation in 2 more places, right? So we make a future here, we append the callback to the future, and we pass that in as the data. And one more time, okay. Thank you. I had that feeling that I was doing something wrong there. All right. You're really paying attention. So that means that this data here is no longer a callback, right? It's a future. And so we don't call it directly, we resolve it, and then it will call all of the callbacks that we've registered. So let's just see, does this still work? Yes, it does. So that's great. Now, as usual, I told you I was going to make things better, but I only made them worse. So just added a few more lines of code. Didn't accomplish anything. Story of my life. So here comes the promised land. The promise is that I don't actually need to create a callback here at all. And I don't need to declare it here. I can combine these 2 functions, and I can just yield f. So that makes this a generator. And somehow, once I'm resumed here, S is writable. So how's that going to work? Well, so quick little refresher here. Everybody knows generators, I know, but like we only sort of know them. So quick refresher. A generator function has the yield keyword in it somewhere, or multiples. It can yield values. And the funny thing about a generator function is that when you call it, it doesn't actually do anything, right? It returns a generator, but it doesn't execute its code. And a generator has some code, right? Interesting. Oh, I know. Right. There it is. And there's 44 bytes in this code. And it has a frame with a instruction pointer. So if we call it, then it actually starts going, and it returns 1 as the return value of that next. And it actually gets going, and its instruction pointer advances. It continues doing that until it raises a stop iteration exception. So somehow we need to kind of run this generator thing to completion. And the way we're going to do that is with a thing called a task. So the task is going to take this generator in, and then somehow it's going to like advance this generator. And when the generator advances, it's going to yield its future object. And so how serious are we that I need to stop right now? Wow, okay. So I was misinformed. So let's just like type for 60 seconds and see the outcome. So sometimes the generator will return. It'll be done. Sometimes we'll need to keep going. And no. Right. So we start off by calling step, and that'll get the generator going. If the generator is done, then we raise stop iteration. Otherwise, we tell the future that we want to resume the generator as soon as it's resolved. And then down here, we wrap the two generators in tasks. If we run this, we'll see that it still works just as well, but awesomely, we've been able to combine these two callbacks into one generator. And we can make the same transformation down here and combine all of this stuff into a single function. So that's how they work. Alas, there's no time for questions, but there's a lot more information at the end of this bit.ly link, bit.ly/coroutines. And if you want to do cool stuff like this, talk at conferences, contribute to open source, go to bit.ly/mongo-jobs. Thanks a lot, guys.